How's it going, everyone? Welcome, Eulier Gonzalez, barely here, but you can see me. And again, as I mentioned in previous videos, yes, I don't have any lights right now, so I'm still waiting for the handyman to come here. Some of you might say, hey, why you don't figure it out for yourself? And I say, yes, but I prefer to dedicate time to recording this series of videos and learn about the particularly JavaScript pillar. So I can now lay out is the structure of this pillar, at least in the synchronous nature of JavaScript, uh, which is the type system, the scope system, as well as the objects oriented system, right? And there is another area in the anatomy of JavaScript, which is the asynchronous nature. So, for example, how now JavaScript deal with the asynchronicity. I'm gonna make a quick recap because this is something that I have done in other videos. All right. So, yeah, again, the way how JavaScript handle this is not per se. JavaScript is a single thread language that what it does is depend of the environment in which it's run, all right, whether it's the browser or the server, like Node.js or any of the IoT devices that use, for example, Node.js to do that, all right? Now is through this particular platform that exposes some of this native or OS functionality, right? So for example, how it handles the asynchronicity is using now timers in the case of callbacks, all right? And we also look at the trade-off of using callback, which is not only is the pyramid of doom, but the thing is that we have to control and coordinate is when these multiple tasks that will be overlapped at a certain point of time, the concurrency, aka, right, when this request will be handled, all right, we talk about time, and when they get, we want to know the proper order in which we actually is emit those tasks, all right, in this concurring order. And then we need to is response back. So we also look at, thanks to Kyle Simpson, how can we do that, and how we can develop that solution, but because it requires you to keep track of the state of the application, as well as to manage time, which time is not an easy thing to do, especially in your applications. That's why we look at thunk. And now, for example, Redux, that has this particular concept called thunk, that say, hey, let's go to now is eliminate time as a concerning factor when dealing with this concurrency. And how it does that? By actually now set a token, all right, or store the functionality into a variable. That variable will act now as a token, so then we can is at some point invoke that or call that variable that hold the functionality, and then we now pass that by the time that we get that data, right? And then we also now more event-based solutions to these problems, such as the promise like, which is pretty much like waiting for the solution. Or again, this video is not talking about promise, but we went about promise, what promise is, what is the problem that promise solve, and how now we can have a particular way of this event driven way of handle single values, all right? And how now, for example, we also we can describe is the data flow in this asynchronous nature, because this particularly is the way how we describe that is not in a synchronous fashion, pretty much like we do when we write any JavaScript statement or when we evaluate an statement or an expression. So statement and expressions here now is an action and a statement invoke an actions, and expressions produce a value, right? So then I also look at the generators and iterators, and what is the main reason of using and looking at this, which give us the ability to pause and resume the execution of a function. Also things like or another interesting question, so for example, like how do we handle is now concurrent tasks or multiple concurrent events or multiple things that happen at a time, all right? So this series of eventual values, that's why we have, for example, observables. And the observables, which is, since this is not native on the language, we look at libraries that can make you, that allow you to, that make it accessible to you. Libraries like the how do you call it, RxJS, as well as another particularly approach of how, for example, in language like Go actually are handling is with this concurrency, right? With a series of eventual values, or in this case, series of computation. Using is the communicational sequence processes, right? So now you're going to handle this data at the application level. Again, this is a concept from Go. But again, what we really care in this video, all right, is that well, the pillar of the JavaScript in the synchronous nature, which is the type system, scope, system, and the objects. We're gonna finally wrap up in today's video the type system. I'm gonna make a quick recap of this, which is the primitive. All right, we got the primitive. Also, we have the behaviors, primitive behaviors, as well as the abstract operations. All right, so the abstract operations, let me change this. Give me a second. And we're back. Yes. So the abstract operations, all right, which is a conceptual algorithm that happens behind the scenes with the JavaScript. That, for example, coercion is one of those algorithms, and the other is the equality, right? And also is the type system, or in other words, is the TypeScript, for example. So first thing first is primitive. So far, primitive, we know what primitives are. So we have the undefined null, symbol, Boolean, string, numbers, and BigInt, all right, as well as object. But object is not a primitive. It's another type of data structure. How can we organize data? So on the primitive, we look is at this nullish values, the undefined and null values, as well as it is operators, all right? So for example, common operators that we might need to use is the nullish coalition, which is these two question marks. Are great for providing you is now default. How do you call it? Default. Jesus. Default. Jesus. Default. Default values. All right. They allow you to do that, to provide you these default values. It's like if any of these, if for some reason the value is a nullish value, well, this will be the default value. Otherwise, assign that value. The other is the optional chaining. You can see that this is to indicate that, hey, if we are trying to access to a property, we need to verify that that property, that value actually exists. It's not a nullish value. If it is, return now an undefined of it. The idea here is that if you use this kind of stuff, it's not quite readable. So I would prefer to use this now, the if statement for that. So it is way much more clear to do that. All right. This is just a suggestions. And the other is a distinction. And how this is something that, for example, if you pass now a default parameter value, and therefore for some reason you need to use that, if you pass now a null as an argument to that parameter, well, what happen is that it's going to be now transform or take that as a null. So to prevent this behavior, we can use is the nullish coalition. Then we look at the another primitive, like the Boolean, true and false. How you can use is the exclamation mark to actually say, well, this is how we're going to flip from one value to another. Then the string, which is a huge universe here, because in JavaScript, since it's using now Unicode, this umbrella term to describe is how computers should render, or is describing how computers are going to encode this character set, all right? Character set encoding, how this computer is going to represent these symbols internally using these encodings. And because there are several of them that falls into the Unicode, you have now USC2, or the most common, which is UTF-16. Since JavaScript use now 68, this is gonna depend of the JavaScript engine, but for example, in V8 is using the UTF-16, which means that this 16 bits that represent is all of the basic multilingual plan, which is a real name, right? So from 0 to all the way up to 65535, all right, which is the entire ones, the entire 16-bit sequence full of one. You now have this representation here. Okay, so that's great, because with that, the idea is that anything that goes beyond that, and since JavaScript use this 16-bit to represent that as as the length of the characters, anything that go beyond that is known as the astral plane, which is a cool name, if I may say. that describe any of these wild icons that we can see, or emojis from that. So that's one of the reasons, for example, when we use now a poop emoji, all right, why we have now the length of 2. Because when you check now is the Unicode that is using, which is this format of U followed by a 4 or 6 characters, all right, since we want to use Unicode to represent that, well, the thing here is now this goes beyond the the basic multiplane plan. So it means that the way it can represent this is by using these two 16-bit known as surrogate pairs or adjacent pair, right? Now, all of this is interesting, is important at least to understand for the emoji or the character evaluation, as we now understand why is this in seems if you look now for another emojis, all right, such as the emoji of the family that now is a collection of these graphemes as they call them, right? So you have now a compositions of all of these graphemes. Now, with that, all right, and we look now at the string behaviors and how these behaviors, all right, is something important to keep in mind. For example, is that how do you describe the characters or a string? How do you have access to the string? Character accessing. How you cannot modify is a string based on it is accessing or property accessors. Also, how you can iterate through this string using now the iterator, which is a series of steps, it's an algorithm to describe how we're going to iterate through any particular data structure, no matter how this weird it is, whether this is a hash map or a linked list, double linked list, a graph or a tree or a graph, all right? We know now an algorithm that is going to walk through each one of them without repeating itself, which is great. Now, why this is important? Because now this algorithm that are built in some objects, or in this case in this primitive, the string, well, is the one to say that allow us to have access to. So using now the for of loop. Now, we can also access to this custom hooks or these hooks, as now the JavaScript or MDN actually talk about that. We can access to these particular hooks that are special in very specific objects that has these particular hooks, all right? Known, the way to access through is via symbols or well-known symbols. This is when you now starting to see all of these weird symbols with that dot, for example, iterate, dot, async iterators, and so on and so forth. It's because of that. It's because they have now internal, symbols allow us is to access to private method or to access to or to define is private properties that the JavaScript engine doesn't generate any value, but internally is keep track of that, which is something that we're gonna see that I hope in this series of videos. So because of that, we were able to now iterate through that or modify the behavior of the iterator by accessing to that, right? So also I look at the string length, the length computation, something important, which is, as we described that, It's also important to anytime you want us to do some sorting, comparison, or length analysis. All right, it is important to normalize this because there's certain element or characters that actually represent more of this Unicode. All right, of this, it contains surrogate pairs, for example. So if you want to now avoid those kind of issues, so you normalize using a particular string that is passed down to. Okay. Now, that's one of the reasons why, for example, we have internationalizations, localizations, how you can use now the internationalizations to say, hey, internationalization API is going to create now a collateral, which is going to define is the alphabet in which we can compare is now words in that particular alphabet, whether it's Chinese, English, French, Spanish, Russian, we can have that, which is a great stuff if you're doing some internationalization applications. The other is the collateral as a way to now detect is meaningful words, or aka words, all right, in a particular body of text. So you can now extract each one of them. For example, let's say you want to do some some text analysis here, right? So it also take in consideration is alphabet that are right to left or left to right. All right, that's also a good thing to know. And I also look now at the string methods. All right, I'm just gonna jump into that. The string methods. All right. The string method, and before another one is the string comparison. It actually follow a particularly and predictable algorithm to that. The string comparison, string equality, string comparison exactly, double, triple, equal, or the obvious that is. I'm not gonna dive deep into much in today's video. The other is the string concatenation, string coercion. All right, well, concatenation and comparison, these two behavior. Okay, and the string methods, we're quite used to do that. So for example, add or char add. The difference is that with add it allows you negative numbers, which is great stuff. We also look at the code point add or code point to actually now identify this is a surrogate pair or not. Okay, and then we look at the substring to actually get that, the index of, the two uppercase to lowercase, to local compare to local lowercase, and so on and so forth, yada yada yada. The concat, all right, the index of, the include, and search. And the difference that is both of them are based on the index of, right? It's say now give me the index of this character that I'm passing here, all right? If it's not, give me a -1. If you do that like an include, it's gonna give you a Boolean, which is great for filtering. If you do now with search, it's gonna find you the first occurrence of that, all right? And it's gonna give you is a number. Or you can also pass is a regular expression to that. Search, unlike match, is that match will give you is all is going to evaluate now a regular expression match, but it's going to give you now is the collections or that, okay, resulting against the original object here. You can say match or match all. All right. We also look at the starting with, end with, padding, uh, pad start, pad end, trim start, trim end, replace as well, normalize, uh, as I mentioned before, to local compare, and then now the string static helpers. For example, if you want to know what is the particular emoji of a given Unicode point, you can do that. Some couple examples, all right? Like line continuation. Another behavior is the escaping characters that you can use, whether it's hexadecimal or Unicode, and how now when it comes to escape multi-character, whether it's using the ASCII, which is hexadecimal, or the or the Unicode, how you can use these now curly braces to actually cover a specific use case, which is that when you pass a Unicode that is more than 4 digits, what happens is that it's going to now coerce, or it's going to evaluate that and not the rest of that, not the 6 not the other characters. So to prevent that, well, we use now curly braces for that. So that is the end of the string, my friend, or at least according to the book that you don't know GS. All right, and then we move now to another huge domain which is very interesting, such as the numbers. And how we need to understand is the way of how these numbers are represented using is the IEEE 7054, which is telling you now how this number is going to look like, right? Internally, how the machine is actually representing all of these particularly numbers inside of your main memory, whether if you're using is a dynamic RAM or a static RAM, right? So one of them using is capacitors, so the other use now is transistors. So if you do the SRAM, right? Synchronous dynamic random access memory, right? Do, do, do. I don't think they describing is what is this made of. All right. Mm-hmm. 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 But I just want to see. Let me ask Claude here quickly. So this is Claude. if DRAM uses capacitor, what SRAM are using? Use transistors. It's interesting. Transistor everywhere. Specifically, is a typically used 6 transistor per memory cell arranged in a flip-flop circuit configuration. Remember that at the end of the day, transistors are help us here, so act like a short circuit, all right, or as an amplifier as well. So transistors are helpful because they can amplify a signal, or exactly, transistors are helpful because they can amplify a signal, or transistors are helpful because they can amplify a signal or improve or act as a switch. Is switching. Can you provide me the source where the spec of static RAM? Okay, can you provide me the source where the spec of RAM said it use transistor? For more authoritarian technical, Wikipedia for real. Tech Target, Electronic Node Engineering Reference, Academy University here. Industry technical papers, bro. Here we go. CT SRAM cell. No, it's made of transistors. What the French does mean? SRAM. Okay. Alright, that's quite interesting. SRAM design leveraging material properties of exploratory transistor. While MOSFET's miniaturization continues to face increased challenges related to process variation, supply voltage, scaling, and leakage current, exploratory devices such as graphene nanoribbon field effect transistor, tunnel field effects transistor, and cardboard nanotube field effects transistor will provide solutions for continuous device scaling with better power performance trade-off. The GaN TFT used in this work, miniaturization. Okay. So, but in any case, according to this, is using this. From where is this? Electronic Notes Engineering Reference. What is a SRAM memory? Is a static RAM. Static RAM or SRAM is a form of computer often used for cache, and particularly in microcontrollers and microprocessors. A typical size often up to 16 megabytes, and there's up to 16 gigabytes or beyond. Mhm. So that's interesting. That's interesting. That's interesting. But again, why am I mentioning here? Because most of the time that data is stored now on a SRAM or a DRAM. Okay, I don't want to go into the details about that, right? I just want to briefly mention when you're using now this spec IEEE 754. This is the way of how now this elements or numbers are represented. Okay, so you have now a mantissa, all right, that is using 52 bits. The other is the exponent, 11 bits, and then you have another sign. Why this is important, you may wonder. Well, because when you're starting to check if a particular number is an integer, or when you want to parse an integer or coerce a number, all right, parsing, you have now two methods: parse int, parse float. The subtle difference in each one of them. For example, parse float, you can use the scientific notations or the dot sign, all right, the dot symbol. But when parse int, when it goes, so it's going to evaluate that particular string until it finds something that is different to a number, right? If it finds a dot, it's going to stop into the dot. If it finds something that is not a number, all right, but it's not if that string that you're passing is not a valid number, parse int, all right, let's say you parse now this like true, all right, you're gonna say, hey, this is not a number. You pass 1, 2, but if you pass a comma, 3, it's going to stop there. But if you pass now an F, it's going to stop until it found any character that is not a number, which is great. But if you want to prevent any weird behavior, confusing behavior, is always preferred to set that radix as 10. Okay, you can indicate that this is 2, the radix 2, or 4, or you want to say, hey, 8, or 16 as well. You want a 16 representation of this, but in our case, just the decimal representation of this, right? We also have parse float, okay, and the coercion of that, and a well-known list of values, especially when you want to coerce those numbers, which is something that we're gonna describe way much more in the abstract operations. Okay, so with that, all right, so this is just a brief introduction of this, and also exploring that we can use other symbol numbers numeric system to represent numbers, whether it's hexadecimal, octal, or binary, as well as decimal, the scientific notation, of course, and how you can improve the readability, especially if you have to represent like long numbers using now an underscore. Okay, so once we understand now how the IEEE works, and it's important because now we can know is how much we can represent here, all right? So the bigger the whole portion, the whole number, the whole part, the smaller the fractional part, and vice versa. And that is useful, at least to understand, because when you want to know how big elements or how big numbers you want to represent, it is roughly to 2 power 23 or 24 minus 1, something like that. But we can do is this, for example, it's roughly this. And this is the maximum number that we can represent, and it is close to that, because if you say, hey, is this 1.79 plus 38 is the same, say number dot max safe integer, or max value is this. This is the maximum number that we can represent, and this number is an integer, right? Number dot is integer, like this. And you have now the number dot max value, right? And it is true. So if you want to know what is the smallest number that you want to represent, it is something roughly like 2. I think is okay. It changed. Okay. You got it. 2 power 2024 and 23 negative, by the way. Something negative. This is roughly the maximum number that we can represent here. Alright. So we can say number dot mean value, alright, which is kind of roughly what that number is. However, if you want to, for example, is now, alright, do some mathematical operations, there is now a particularly number that allows to represent that, the maximum number that we can represent when we're doing this mathematical operation. And this is, so for example, any mathematical operation is like a sum, alright, or a subtraction, division, multiplication, basic arithmetic, alright. And for example, alright, let me put it this way. For example, if we need to do is this, number dot, we get access to the maximum value that we can represent, which is max safe integer that we can represent, alright? So if for some reason we want us to now do mathematical operations with these max safe integers and add one, we can do that. As you can see, it's actually give you that, or this. But hey, there is something wrong here. It's actually giving you is the same number. It's doing this because the internal representation, when it's doing this operations, and since this is the maximum length or the maximum safe integers that it used to say, hey, this is we say this is maximum because we can guarantee is the accurate of these numbers way beyond that. And you may say, accurate, what in the F does it mean? So can you accurately say or tell me what is the 1 divided by 3? All right, and by accurate, I want you to give me is a single number, period. And in this case, it gives you now 0.33333. And when we say accurate is, say, for example, numbers like 1 divided by 2, all right? When it actually is something that you can represent here, So you say, hey, parse int, okay. Since this is gonna give me now is a yes, and this is gonna give me now an int. So I'm gonna use now a float for a moment. So on this, all right. And then I want to parse that, all right, to string, and say parse this to string with the radix 2, all right, or 4, or 2, right? So the point of this is that this is an operation that you can represent accurately, or it has now a fixed dimension, it has a fixed length here. But the problem with 1 divided by 3 is that this doesn't have a fixed way to represent this. So this is when now interview questions like 1.1 plus 0.2, it actually comes here, because it says that, hey, we have now this particularly, we cannot accurately represent in 0.1 plus 0.2 first, all right? So we need to round that behind the scenes, okay? And anytime that we round it, because we want it to now make it fit, we want to fit this number, this representation in this 64 sequence, all right, of a slot. Because of that, and since our memory is limited, well, the best thing that we can do is to now try to run these particular operations, right? So in other words, it's trying to say parse int all right. Instead, it's trying to parse in. Okay, exactly. This is if he wants to parse in this. Okay. Okay. Again, because this number representation, this is one of the reasons why I actually pulled this up here as an example of that, especially to actually understand that particular behavior. Okay, since the representation of 0.1 and 0.2 are not accurate, all right, this binary representation of these two numbers, they are not the same. Okay, 0.21 and 0.2 they are not cannot be represented correctly. Not to mention this. So because of that, the idea of this is to recognize that this is something that happens in the language, and the solutions to that is to avoid any floating operations in any language that uses IEEE. One of the solutions that actually use Stripe is to say, hey, let's go into now is perform including the decimal in as a whole number, and then now once that is done, all right, so transform the string into a the send, just like that. So this is one particular solution that they use it for. We also look at the, for example, values like positive, negative, 0, how you can use that, when you can use it. The other is nan. Why nan actually is is important to have in the language, because you can ask yourself, is like, how do you represent the result of a mathematical operation that is invalid? You can use null and undefined, but if you do, that's actually not what it means. It's in fact, it's weird. Another thing is to say, hey, I can use a try and catch, but again, that's not actually quite helpful to do so. All right. So what you can do? That's a good question. Well, here you can use this now, the epsilon imprecision. All right. If you can avoid floating points by scaling all the way up to a whole number of BigInt while performing math, do so. That's the TLDR of numeric things and so on and so forth. What is the another one? Because this is something that we're going to explore in today's video, is now the epsilon threshold. So a common piece of advice to work such floating point imprecision, use this very small number value defined. So epsilon is the smallest difference JavaScript can represent between 1 and the next value greater than 1. All right? Which is almost, is the, okay. The idea of this epsilon, all right, is to, I think that is to understand how that works, is to understand what it is. Epsilon is the smallest difference JavaScript can represent between 1 and the next value greater than 1. The idea of this is to, especially if you need to work with this point flowing operation, is to avoid them. Avoid using, convert or scaling them into whole numbers or BigInt while performing math. If you can do that, do it. Do it. That's all. We also look at the numeric comparison. All right. The numeric equality. Just like a string, numeric comparison for numbers use either the double or triple equal operator or object that is. Also recall that if the type of both operands are the same, the double operator performs identically to the 3 equal, 42 and 42, 42, 42, which is gray, is even here. So numeric comparison, the numeric relational comparison, so numeric, let me actually, exactly. So numeric comparison, all right. And here in the numeric comparison, we have stuff like the the numeric comparison. We have stuff like this actually the same. So double equal, triple equals, an object that is all also recall that if the type of the both operands are the same, perform identically to the triple equal. So there is no things behind that. For double equal, coercive equality, when the operand type don't match, if either operand is not a string value, prefer numeric equality, check. Exactly. Numeric, not a string, is going to now is coerce that into that. But again, this is something that we're going to see that later. numeric comparison, numeric equality, okay, numeric equality, and the other is the numeric relational comparison. All right, I think both of them are quite interesting to do so. 42, 42, so they're gonna behave as expected. Numeric comparison, and the other is a numeric. So we have now the numeric equality and the numeric relational. So for example, here we have stuff like wait, what? So for example, like this. And the numeric relational comparison, like this. Remember, just like double equal, also coheres. This is also important to know. These operations also coheres, meaning that any non-number values are coheres to numbers, unless both operands are already strings, as we saw earlier. They are not strict relationship comparison operators. If you're doing relational comparison between numbers, the only way to avoid cohesion is to ensure the comparison that the comparison have always two numbers. Otherwise, these operations will do coercive relational comparison, similar to how double equal perform coercive equality comparison. So it's because of this. It's because also it's doing coercion, it's also doing that coercion. It's also doing that coercion. Mathematical operations here. It's also doing that coercion. As I assert early, exact mathematical operation. As I assert early, the main reason to have number in a programming language is to perform mathematical operations with them. So let's talk about how do we do. Exactly. Well, I think this is quite obvious. Okay, these mathematical operations are binary, meaning they expect two values operands to do that. They all expect the operands to be a number values if either of both operands are non-numbers. Because of this, it's gonna also coerce the unity operators. As you can see, white space or even new lines are allowed between unity operator. This is true on all operators and operands, increment and decrement. I think this is quite interesting here with mathematical operators. Okay, especially here, this mathematical operators. Okay. What the French toast? these mathematical operators. Okay. So for example, arithmetics, all right? We're quite familiar with arithmetic, all right? Arithmetic and plus and negative, all right? So arithmetic operation, all right? So arithmetic operations like this may be quite silly to get it, but it's important to know. And also is negative, even that it is a string, because it's going to coerce that. You know, even with a string, it's going to coerce that. That's interesting. Even with a string, it's gonna coerce that with these operators, bro. Increment and decrement. Exactly. So increment and decrement, something that we all are quite familiar with. Increment and decrement. All right. So for example, here and the other one, and it all starts with this. And it all starts with this. However, these are a special operator in the way that they can appear to perform is the boxes and the operand position. It may seem peculiar that prefix and post position seems to give the same result, incrementing or decrementing in such example. The difference is subtle and it is related to the final reassignment result. We'll revisit this particular operator in later chapter to get into this. But again, it's quite important to understand that the increment and the decrement, right? And whether it's the postfix and prefix, which is now is telling you is when is going to the assignment occur. All right, I'm going to increment this number, but I'm not going to. So for example, if you do this here with the positive, you say, hey, I'm going to increment that number especially with variables. You say num 32. All right, so I'm going to now is increment that value and assign to, whereas if I call now num again, but if I say now num and I do the postfix, I'm gonna say, hey, I'm gonna decrement these numbers, all right, and not reassign that. Okay, I'm gonna decrement this number and I'm gonna return is the old value. That's what it is. That's what it is, man. So when you do this, you're saying, hey, I'm going to increment those numbers and I'm gonna increment the number, but I'm going to return you the old value, which is in this case 32. Oh, it's the old value that it has. So right now the current value that this number has is 32. So if I do this, it say, hey, I'm going to increment is this value, but I'm gonna return you is the old value. And you may wonder, when do I need to use this? That's a very good question. There might be some scenarios that you need to get the there might some scenarios that you need the old value first, And then the increment, others you want is the increment right away, all right, with the postfix, okay? It's like, no. I want the value right away, bro. I want the value right away. I want the value right away. Okay, cool. All right. All right. We did a little bit of house cleaning, that kind of stuff. Bitwise operators, stuff like that. Yeah. Just like any other primitive operators, this is now bitwise operators. JavaScript provides several bitwise operators to perform bit levels operations on numbers values. However, these bit operations are not performed against the bit pattern of IEEE 754 numbers. See chapter 1. Instead, the operand's number is first converted to 32 bits integer. Okay. JavaScript provides several bitwise operators to perform bit level operations on numbers value. Bitwise operations on numbers value. However, these bit operations are not performed against the bit pattern of IEEE 754 numbers. Instead, the operand number is first converted to a 32-bit signed integer. Interesting. The bit operation is performed, and then the result is converted back into IEEE 754 number. Keep in mind, just like any other primitive operator, this just compute new values, no actual modifying a value in place. Okay, so bitwise operators, this compute is new values, all right? Bitwise operator. I am definitely not someone that are quite too used to this. So this might just boost your ego and see that how clever you are. But again, improves the readability of your code. Is what it is, man. Deal with that, man. If you wanna do this kind of trick and stuff like that, I'll invite you to go with Haskell. All right, to actually test your might. Test your might. You get it. Test your might. Keep in mind, just like any other primitive operand, these just compute new values. Alright, so we have bitwise performs an AND operation with each corresponding bit from the two operands 42 and 32 are equal to 32, it is they are converted into that binary representation. Okay, bitwise operators. So performs an AND operation with each corresponding bit from the two operands. Okay, and here is where now the mathematical aspect of this actually shine. So if you know that 3 and 3 will give you this, because you know that it's going to perform is the AND operator, all right? So you can say that 6 might give you the 6 as well, all right? But what about 12 or 12 and 6, right? What about 12 and 6, right? Okay, so this is gonna give you is this 4, all right, which is converted into 32-bit signs. It operates that operations and then give you now the result into IEEE 7054. So one of them is operating is an AND, the other is OR, all right? And it means that it's going to only take those value slots where both of them are 1. And here, with an OR, it's gonna say, you're gonna take all the values, you're gonna fill all the values with 1, except if I found is double zeros in those positions, which is this. So this is if you want to, okay, that's interesting. The other is the SOR operator. Not quite familiar with the SOR operator. Right, bitwise not. Left shift. Perform a left shift of the bit of the operand here. Oh, exactly. So left shift bitwise operator. So you say, hey, now shift the bit 3 places. So if you say this, all right. If you say this, you say, hey, now shift this value, this 2, all right, or this 1, 3 positions. You say 1, exactly. Say 0, 1, 2, and 3, all right. So 2 power 3 actually is give you, it's like say 2 power 8. This is the same. If you do this, is that now shift this 2 operands 3 position, which is now say, hey, this 3 is going to be move on to 3 positions. So from this 3 position now it's going to move down to 0, 1, 2, 3. 3 representing 8, and 2, and the next one, which is 1, represent is 2 power 3 and 2 power 4. Two power 4. Is 16. Oh, it's because it's okay. It's because that number is converting to 30 bits, then perform the operations, and then okay. That number, which is an IEEE 74, is converting to 32-bit, perform the operation, and then return it back as an IEEE 74. Holy shit. So here, if you say this, shift to the left 3, of course, now it's gonna say 16. Exactly. Hey, now I want you to shift is 3, which represent is that, and that actually is gonna be is 24. Exactly. And so on and so forth, as you can see, right? But it's interesting. Bitwise operator. Okay. Operadores a nivel de bit. God damn it. Mm-hmm. Mm-hmm. But I think this is important at least to know them, right? Bitwise operators here. Bitwise operators. That's interesting. That's interesting. You know, it's logical. It's follow a series of steps. It just follow a series of steps, bro. It follow a predictable series of steps, bro. Number value method. Number value provide the following method as property for number specific operations to exponential, to fixed, and to precision. And there you go. Number value method. Here we are. Number value method. Do you know that I was able to Jesus Christ. You know, it's okay. It's okay. So to exponential, oh my God. Okay. Okay, that's okay. That's quite the. That's quite the. But you can do this. You can say, hey, 42. To exponential. I think this is one of the beautiful stuff of this. All right. At least of JavaScript, of this dynamic nature. What we're doing here is boxing. So it now temporarily hold that object, or it now temporarily is wrap that object with this property. So it temporarily wrap that value in an object to check if that is a known method for that specific value, for that specific primitive. And in this case, this is a number. Yeah, you do. So it's going to do that. To exponential, right? Say 2, but it's an invalid expression. That's okay. So I expect you to exponential 2, say 2.2 e plus 1, right? This is a static method? How do you use this? To exponential? Invalid or unexpected token. No, it's because I don't know how to use this. To exponential. Exponential. Okay, to exponential. Return parse flow to exponential. Okay, it's just a single number. Okay. To exponential. No? What about if we do this? To exponential. But I think this is for point floating. Point floating operations. So you say, I don't know, GPA, some fraction. Come on, I got all of. How can I clear this, bro? I don't have any. So fraction is 42.42. And then I say fraction of the 2 exponential and say 3. Fraction to exponential is not a function. To exponent, because I misspelled that. To exponential of 3 All right, or you say 1. To transform that into an exponential like this, and when you do something like parse float of this exponent, you'd say now this is 42. Exactly. So okay, it transformed that into an exponential. Produce a string representation of a number using a scientific notation. To fix, produce a non-scientific notation string representation of the number with a specified number of decimal place, random or zero padding as necessary. So for example, if you say, hey, 16, say 16, all right, and then I say, hey, parse int this string, and it's important to pass the radix to avoid any confusion behavior. Parse int, and then I want to somehow transform this. Let's say we got now this 24. I want to transform that into now a string of radix 2. Alright, want to parse that into 2. It say give me 2. I don't know why. What if I say this? Alright. Exactly. And this is you produce a non-scientific notation of that. To fix, to precision is like to fix, except to it applies the numeric argument as the number of significant digits, including both the whole number and decimal place, if any. And so you say 42.42, okay, and then you want to access to precision. To say now give me is a string, all right, where you include now all of them, all right, with the number of significant digits, but it's gonna produce you a string for that. Produce me a string that includes all the significant digits into locale string. Okay, to say, hey, I want to represent now this number to locale string. Okay, this local representation of this to locale string. To local string. Invalid when respecting token. Invalid when respected token. According to the current locale. Okay. Or you can say fraction and to locale. All right. Okay. But this is the number valid methods. To exponential, to fix. I'm not quite familiar with this, even though to exponential is converted into a scientific notation. To fix is give me this in a non-scientific notation. And the other is the precision. To say is like, hey, give me now is the significant digits here. To locale and all that kind of stuff, bro. The significant digits to it. All right. Okay. the significant digits to this. So something that I'm quite familiar with, the significant digits to this. And then you have now the static number properties, right? Static number property. The number epsilon, the number dot nan, the number dot mean safe integers, the max safe integer, the positive and negative integers with the largest absolute value further from 0. Okay. And the static number helpers. The static number properties and the static number helpers here, as we look that it exists. Okay. And then another is, well, the math operations. Static math namespace. Since the main uses of number values is to perform in mathematical operations, JavaScript includes many standard mathematical concepts and utility of the math namespace. For example, math.py, math.apps, math.round, math.mean. Unlike number, which is also the number function for number coercion, math is just an object that holds this property and a static function's utility. It cannot be called as a function. One peculiar member of the math namespace is math.random for producing a random floating point values between 0 and 1.0. It is unusual to consider a random number generation a task that's inherently state UI side effecting as a mathematical operation. It also long been a footnote security wise as pseudo-random numbers generators. That JavaScript use is not secure and can be predicted. From a cryptography perspective, the web platform stepped in several years ago with a safer crypto get random values API based on a better PRNG pseudo-random number generator, which fills a type array with random bits that can be interpreted as one or more integers of type specified maximum magnitude. Using math.random is universally discouraged now, but now it's using is this crypto get random values. Crypto get random values. So crypto get random values. So here's the crypto get random values. And what this produce, bro? Fail to execute get random values on crypto. One argument required, but only 0 present. And what is that value? An array. An array of 1, 2, 3. It's not a type array. Parameter 1 is not a type of array buffer view. What the fuck? Crypto get random. Crypto random UI. So get random values, or get random values here. Type array. Method like cryptography store random values that are given as a parameter. It's filled with random number. It is cryptography meaning. To guarantee enough performance, implementation are not using a truly random number generator, but they are using a pseudo-random number generator seed with a value with enough entropy that pseudo-random number generator algorithm may vary across user agents, but is suitable for cryptography purpose. An integer base that is one. Okay. That's going to create our own. It's going to create our own. Exactly. It's going to create our own. This is very narrow specific stuff here. But if you want to make use of this, where you say crypto get random values, and here I want to now specify is this new array reserving space in memory for this unsigned integer 16 bits array, alright, that I want to represent is the value here of, let's say, 16, alright, and then I want to store this as an array, say const array, and then I want to console log is the array to see what is the value there, and then I'm going to pass this array to this. So here we create now an unsigned 32. Alright, we create an unsigned 32 with the value 16, and of course modify that, so okay. So what we can do here, let's go again. Okay, good. So I want to create now is this 32 array with 16 value, where what I'm gonna do first is to see what is the length of it, but I don't want to be too long, so I want to be more like this. And so then I want to store now the value 8 here, so you're gonna see this 8-bit value that in the middle is supposed to store that as 1. Alright, that's quite interesting. Well. Oh no, I am indicating is the length. My bad. Okay. Good. No, that's okay. I'm indicating here is the length of this. Okay. In other words, if I say, for example, like 4 of 16, what I'm indicating is that at that position, let's say array 0, what's going to do is this. Array 2, I want to store now a value of 15. Okay. And if I navigate to that, which means is that get into the console log and see, I got the value 15. If for some reason I want to say, hey, now I want to have access to the same location, and therefore I say 16 is gonna say good, alright, but now I need to use some additional space for that, which is on the array, right? We say, no, I can store this as 16, which is great. Awesome. So what if I told you something like this? 17. Right, then I want to console log that again. It's still storing that. So that's interesting. That's interesting. It's using now an unsigned 16, where each one of those is using now 16 element. Oh, I get it. I French toes get it. I French toes get it. So if I tell him like this, which I assuming that this is the minimum array that you can have, exactly. If I say this, and I want to be of 4, and if I tell them that each one of those slots now represent is 8-bit, and then in the middle I want to represent something like this, which go beyond that, what will be the expected output? Well, so the expected output here will be is that I won't able to store that 256. All right. I won't be able to store that 256 in that position. All right. So you may say, why not? All right. So I want you to do, for example, 255, right? And then console the log. So I want to get into that. Oh my God, is this? And then he say, okay, now I can represent that. But it's interesting because anything that goes beyond that, it's a, I'm not gonna do that. Anything that goes beyond that, say 256 or 257, and it say, well, now I'm gonna use this as a way to represent that, right? You know? And that's perhaps the beautiful stuff of this. So if you are going to create now a new array, say new array or unsigned 32 unsigned integer, okay, unsigned integer of 30 of 16 array, where I want you to create now is just 4. Can say new array, okay, and then somehow I want to say is, hey, new array at that position, I want in the middle of the position I want to be is something for like 65 5 3 4 5, and then I want to console log that the new array. What will be the expected output? Well, that position, it represents that correctly. Exactly. So if I put now 6, for example, it say no, I cannot represent that, so therefore is 0. You know, that's the whole idea of this integer array. But again, it needs this unsigned array. That's the whole point of this. It needs a new array of that. Throw in the byte length of type array exceeds 65, because the length of that, the byte length of this type of arrays can be expressed in 16-bit. So this is how you can now create this. Okay, we clean up here a little bit. Okay, and once you get access to that, you say now crypto get random values, and then you pass now the array. You're gonna create is a new collection of random values here, all of them are guaranteed to be random, which is great. All right, this is how you can create your own lottery. Okay. So there is no minimum degree of entropy mandate of the web cryptography specification. User agents are instead urged to provide the best entropy they can when generating random numbers using a well-defined, efficient pseudo-random number generation built into a user agent itself, but seeds with values taken from an external source of pseudo-random numbers. So in other words, if you want exactly, so your lucky number is this is how you can create this lottery, right? So this is the lucky numbers. And is this? Most of the time, this is web cryptography level 2, and I think this is from that. From the specification of that web cryptography API. That's interesting. That's interesting. Very, very interesting here. Very, very interesting. JavaScript object signing and encryption. Jose. Jose. Okay. Interesting. But again, we look also is how you can now generate is random numbers, okay, and the static math namespace. Why the static math namespace exists, so we can perform at least is basic operations, you know. So we can perform some mathematical operations, right? Some mathematical operation. If you take a look now at the math object, okay, in JavaScript, there is a ton of things that you can do here, right? Min, max are the most common one, as well as get the square, some precise, tangent, trunk, so on and so forth. Log 2, log 10. ln2, logarithm 10. But as you can see, this is like quite most of the mathematical that you can get, you know. So the most common math operations that we can get, all right, in randomness. In our case, it's preferred to use now crypto get random values, okay, because the JavaScript is not secure and which means it cannot predict. From a cryptography perspective, the web standard stepped in several years ago with a Saber Crypto Random Values API based on a better pseudo-random number generator. Exactly. As a mathematical operation, it's also a long being foot gun security-wise. It's a foot gun security-wise, man. Especially this. Randomness. So math random has been a foot gun security-wise, as a pseudo-random number generator PRNG that GS use is not secure and can be predicted. From a cryptography perspective, the web platform stepped in several years ago and encouraged you to use now the crypto to get random values by passing now is a finite collections of type arrays, all right, or unsigned or integers, unsigned integers value for that. All right, so far so good. BigInt and numbers don't mix. All right, they cannot perform operations on that. Okay, so BigInt and numbers don't mix. Keep in mind that coercion between this type has some risk as well. Now that we look at all of this, primitives are foundational. Over the last two chapters, we dug deep into how primitive values behave in JavaScript, and I bet more than a few readers were like me ready to skip over this topic, but now hopefully you see the importance of understanding this concept. Not only that you already have the structure, and anytime what you need to do is just to update that structure, update, remove, and so on and so forth. That's quite interesting here. Twitter community here. New update to the Twitter text library emoji character count. In 2018, Twitter text of library of conform and test standardized parsing of text of tweet text is synchronized, developing, testing, creating issues, and so on and so forth. Developer Twitter.com. Developers, documentation, forums, and blog. Tap into what's happening to build what's next. Use cases, build for business, build for the public, do research, touch and learn, build for fun, build for good, build for business. Listen to the conversation on X. Monitor your brand, track events, use insight from X, manage your social media, oversees customer care, uncover consumer insight, inform search result, research marketer and audience, build for publisher, embedding X content, research market and audience. Research market and audience. So I think they must provide an API for that. Research markets and audience is because it's huge. It's huge, bro. It's huge, bro. It's huge, bro. X API, X at API, tutorials. A user post and mention with the X API version 2. Use case, successful stories. Audience por Banco Pichincha. Banco Pichincha use audience managers and network graph analysis functions of Audience Connect to create custom audience of creators and amplifiers. We talk to everyone, our brand audience, and a whole lot of more, but through media. We target only those creators and amplify that allow us to reach the audience we want. Banco Pichincha is something. I think Banco Pichincha is from Mexico. No, but Banco Pichincha. Banco Pichincha is something from Colombia. I think it is, or Ecuador. Ecuador. Banco Pichincha. Exactly. Banco Pichincha. Interesting. All right. Mm-hmm. Mm-hmm. Bill for businesses. Okay. That's interesting. Oops, I think I close that. Mm-hmm. All right. Mm. Mm-hmm. Primitive are foundational. So primitive are foundational. And yeah, go back to this, to the primitive. Multi-character escape, then play literal, and then we can go to the big integer values, right? Big integers values here. Big integers value. There is no big integers behaviors, which is quite interesting, or at least not defined by him. Mm-hmm. For the reason exactly as the maximum safe integer in JavaScript is this 9 quadrillion or 9 followed by 15 digits. Such a relative low limit can represent a problem in JavaScript programs. Need to perform larger integer math, or even just whole values like 64 integers ID, Twitter tweets ID, for example. For that reason, JavaScript provides the alternative BigInt, high big integer, which can store arbitrarily large, theoretically non-limited, except by finite machine memory and or JavaScript implementations integer. To distinguish BigInt from a whole integer number value, which will otherwise both look the same, 42, JavaScript require an end suffix to the BigInt. But (64-bit integers), exactly 64-bit integers. 64-bit integers. Exactly, or just whole values like 64-bit integers. To illustrate the upper bound of BigInt is this. You can represent that. And even you can add or do more operations on this BigInt, and then you won't have any of this issue. question is, can you transform that into BigInt? Okay. But if you store that into a number here, and you say number, okay. Now you have to, okay. You have to take that value physically, like that. And they are now able to perform that kind of operation. Is able to do precise arithmetic above the integer limit to the number value type. Notice that the plus operator requires, instead of just this, but what is doing behind the scenes here? See above, such a relative low limited problem is in JavaScript. For that reason, JavaScript provides an alternative big integer which can store arbitrary large, theoretically not limited, except by finite machine memory and or GS implementation. Okay, it can store arbitrary large, theoretically not limited, except by finite machine memory. So they are now limited by finite machines memory. So this is the longest string that it can be, and even though it cut that off, and it's interesting because it's not all of that, because more than that, it is a point that now what it does is to compress those numbers. You know, it reached to a point that it now compresses those numbers. It reached to a point that it compressed those numbers. Or huge int. To string, exactly. And you want to know the length of this is now a 9060 digit here. All right. Notice that the plus operator requires that both of these are like that as BigInt. Do not mix them. They cannot be mixed. It may seem counterintuitive to some reader. BigInt is always called without the new keyword. If new is used, an exception will be thrown. But that's not uncommon to represent large integer values as string, especially if those values are coming from the JavaScript environment, from other languages environment, or by a certain exchange format, which themselves do not support BigInt style values. As such, BigInt is useful to coerce those string values to BigInt. Unlike parseInt, if any character in the string is non-numeric, 0 to 9 digits, including points or even the trailing end suffix character, an exception will be thrown. In other words, BigInt is an all or nothing coercion conversion parsing. I think it is absurd that BigInt won't accept the trailing end character while string coercion and thus effectively ignores it. I lobby vehemently for that behavior in the TC39 process, but was ultimately denied. In my opinion, it is not a tiny little gotcha one on JavaScript, but a warrant nonetheless. Symbol values. The symbol type contains special opaque values called symbol. These values can only be created by the symbol function. Finally, we're gonna talk about what we want here in here. Okay. Okay. So if you want to represent now numbers bigger than the safe integers in operation, okay, you want to do that, you can. All right, and for that reason JavaScript provides is this particular alternative. And not only that, is that you can also perform operations to that, arithmetic operations too. Can also be created with a BigInt function. For example, like this, to convert a number into a exact, which is now number cohort exactly. Number or BigInt conversion. BigInt conversion. And then now we reach to this symbol. Okay, here we go. Here we go with the symbol. Symbol values. The symbol value type contains special opaque values called symbol. These values can only be created by the symbol function. Secret, symbol, my secret. Just as BigInt, the symbol function must be created without a new keyword. The my secret string passed into the symbol function called is not the symbol value itself. Even though it seems that way, it is merely an optional descriptive label, used only for debugging purpose for the benefit of the developer. The underlying value returned from symbol is a special kind of value that resists the program developers inspecting anything about its underlying representation. That's what I mean by opaque. Because U is a special kind of value that you can inspect the underlying representation. You could think of symbols as there are monotonically incrementing integer numbers. Indeed, that is similar to how at least some JavaScript engine implement them. But the JavaScript engine will never expose any representations of a symbol underlying value in any way that you or the program can see. Symbols are guaranteed by the JavaScript engine to be unique only within the program itself and are unguessable. In other words, a duplicate symbol's value can never be created in a program. You might be wondering at this point what symbols are used for. That's a good example, and I know what they are used for. One typical use is as a special value that the developer distinguishes from any other values that could accidentally collide. For example, you set this as empty, not set yet, and then you later on want to check if that is equal to that. Here I have defined a special empty value and initialize my nickname to it later. I check to see if it is still that special value and then perform some action if so. It might not want to have used null or undefined for such purpose, as another developer might be able to pass in one of those common built-in values. Empty by contrast here is a unique, unguessable value that only I have defined and have control over the access to. Perhaps even more commonly, symbols are often used as special meta properties on objects. So for example, like this. where you are going to now pass is this particular value, symbol, private unique ID, don't touch it. It is important to know that symbols property are still publicly visible on any object. They are not actually private, but they are treated as a special and set apart from the normal collections of object property. If it is similar, I have to do this myself. My info, private ID, don't touch me. Let's go to do this, shall we? All right. So if I do object.define property, my info, which is now this, it holds this value, and this is now the objects built-in that it needs. So value, enumerable, mechanism. By convention only, most developers know that if a property name is prefixed with lowercase, or even more so, that means it is pseudo-private, and to leave it alone unless they are really supposed to access it. Symbols basically serve the same use case, but a bit more ergonomically than the prefixing approach. Well-known symbols like this. Oh, and here we go, the well-known symbols. So let me now do is this first. Let me actually check this, info, and I get a stuff. My info private to generate that ID, right? And if for some reason try to access to that, okay, that of course, it is opaque. I cannot inspect that from the developer perspective, yet the value exists. Okay, yet the value exists. Reference error, generate ID is not defined, of course, but imagine that you do. And then you have now the well-known symbols. JavaScript predefined a set of symbols referred to as well-known symbols. They represent certain special meta-programming hooks on objects, and these symbols are stored as a static property on the symbol function object. So for example, these symbols are stored as a static property on the symbol function object. Okay, as the static property on the symbol function object. This is known as well-known symbols, like a hash table of this. And they allow you to have access to certain kind of stuff. So for example, to say, hey, I want to now to tag the string here with this. Symbol.string tag is a well-known symbol for accessing and overriding the default string representation of a plain object, replacing the object part with a different value. So for example, my info. See the object and classes book in this series for more information about well-known symbols and meta programming. So for example, in this, I don't know if he actually could dive deep into this. All right. Exactly. Listing all containers content, temporary containers, format values, 1, 2, 3. Containers are collections of properties. And then you have now how objects works. Property. This is quite important to understand this. Default if omitted, accessor properties, object subtypes, arrays, empty slab and functions, object characteristics, and I think it stopped this. And the prototype changed. The constructor prototype to string and has on, creating an object with a different prototype. Exactly, something that I'm quite familiar with. The empty prototype versus prototype and the object's behaviors. And then you have now the other one, which is classy objects. Keep it classy, right? The constructor, node, class method, class instance this, public fields, and then you got this, avoid this pattern. And the class extensions and how that works. Good. Inheriting is sharing, not copying. Inheriting is sharing, not copying. Exactly. Static class behaviors, static property initialization, static inheritance, exfiltration, private classic examples. To describe now this. And then you have another chapter 4, which is this word, added this. Default context invocation, explicit content. This is run. Okay. And then you took now at the delegation here. The new factoring, so on and so forth. Okay, that's going to the objects and classes, but again, we are about to wrap up this section, or at least today's video is by now looking at the bit integers values and the symbols. You know, here at symbols, symbol values, especially here, you know, symbol values, and how now symbols values, the TLDR of this is that you can think of symbols. So it is called opaque for that. So the underlying value of symbols are called opaque. Symbols are called opaque for that. That is because that internal representations of that. And the other is the well-known symbols, which allow you to, it represents specific meta programming here. And the other is the well-known symbols, bro. Symbols values and the well-known symbols that this actually represent is metadata, represent certain special meta programming hooks on objects. All right. Global symbol registry that you got is this. Often you want to keep symbols values private, such as inside of a model scope, but occasionally you want to expose them so they are accessible globally through all the files. Instead of just attaching them as a global variable, property of the global this, JavaScript provides an alternative global namespace to register a symbol. Holy fuck. An alternative global namespace to register symbols. So JavaScript, okay, so JavaScript provides an alternative, JavaScript provides an alternate global namespace, bro, to register these symbols. Symbol for private ID and symbol for key for off. The value passed for symbol for is a namespace. It's a particular namespace, bro. Okay. It's a particular namespace here. Okay, for storing private stuff here. And then you got now the objects or primitive. Unlike other primitive like 42, where you can create multiple copies of the same value, symbols do act more like a specific object's reference in that there is always complete unique for purpose of value assignment and equality comparison. The specification also categorizes the symbol function under the fundamental object section, calling them the function a construction, and even defining its prototype type. However, as I mentioned earlier, new cannot be used with symbol. This is similar to BigInt constructor. We clearly know BigInt values are primitive, so symbol values seems to be the same kind. And in the specification terms of definition, it lists symbols as a primitive value. And moreover, the values themselves are used in JavaScript programs are primitive rather than objects. For example, symbols are primarily used as key in objects. We know object cannot use the other values as key, along with strings, which are also primitive. As mentioned earlier, some JavaScript engine even internally implement symbol as unique, monotonically incrementing integers, primitive. Finally, as explained at the top of this chapter, we know primitive values are not allowed to have property set on them, but are out of boxes, automatic objects, internally to corresponding object wrapper type to facilitate property method access. Symbol followed as the exact behavior, the same as all of the other primitive. At this considered, I think symbols are much more like primitive than object. So that's how I present them in this book. Okay. So that'll be all for this video. Take care.